Welcome back. This is part 2 DFT chapter 6.1.1. In chapter 6.1, we'll go through the following introduction to DTFT. We'll show that DTFT is a transformation. We'll discuss different types of discrete time Fourier transform, and we'll see DTFS from a linear algebra perspective. Why DTFT? Basically, all real-world signals are digital. Audios communicated through Zoom via the digital cameras are sampled sequences. In addition, that time is an integer where we are sampled time xn equals to 0, 1, 2. Not only that, the values of xn are actually numbers with finite precision. In these particular lectures, we are not going to deal with finite precision effects. We'll mainly study how to process digital signals xn of sampled real-time signals. DTFT applies Fourier transform on discrete sequences. DTFT can be used to analyze aperiodic signal as well as periodic signal. This is as opposed to DTFS, discrete time Fourier series, which only applies on periodic signals. Why another Fourier transform? Why another transform if we already have Z transform? Well, like the Z transform, Fourier transform can decompose signals into the frequency domain, representing them as sum of complex exponential. And when we do that, we are allowed to manipulate these signals via the frequency representations. Additionally, we can generate features for classifications, and convolution in time becomes multiplication in frequencies. So these are some of the main reasons why Fourier transform exists, even though Z transform exists. There are many other properties which are useful: linearity, time delay, time scaling, modulation, and differentiation. In the Fourier domain, it becomes simpler, allowing the signal to be manipulated in the frequency domain much more easily. This diagram shows linearity and time invariant systems and what is it in for us when we study it using the frequency domain. The signal X is composed of three signals: A1, e.g. omega 1, a complex exponential at omega 1 frequency with amplitude A1. It has also A2 at omega 2 and A3 at omega 3. They are all summed up together, so Xn is a complicated signal. They are then sent to a linear time invariant system with impulse response Hn and outcomes Yn. Now, you can study the system in this way, or alternatively, because the system is linear, you can actually break down the signal individually and then study each individual impulse response, each individual signal's response. So A1 omega 1 becomes B1 omega 1. So what happened? The signal A1 changes amplitude to B1 through this system. Why? Because the system's frequency response has this behavior. At omega 1, the frequency omega 1, it will modify amplitude A1 into B1. So it has a gain at omega 1 such that it will be B1 divided by A1. So if A1 is 1, then whatever B1 is the absolute gain. Similarly, we have omega 2 and we have A2. Again, the gain at omega 2 is B2 over A2. Now, what will happen is that the gain is not only a magnitude, it has a phase as well. So you will change the absolute value of the signal by this magnitude, and it will shift the exponential by this theta. So that's the idea. So in linear time invariant system, we can break the signal into small parts and analyze them in this part. And what we then have is something called the frequency response. The response at omega 1 omega 2, omega 3. In fact, you can plot all of omega, and therefore you will know what will happen at different amplitudes. Sorry, at different frequency you have what different amplitude, and you have different phase at these particular frequencies. That's the frequency response idea when we analyze signal in the frequency domain. And DTFT allow us to do that. The other way to realize it is that DTFT is a special case of the Z transform, because DTFT only analyze the frequency. Imagine this is the frequency, the Z domain, the Z transform, where this is the Z and this is the unit circle. Then we are only actually analyzing along this green ring, which is the discrete time Fourier transform. So later on we will give you more details about that. The next picture tells us about DTFT as a transformation. We have seen in the time domain when we have x of t, we have the impulse response, and convolution in time becomes, the processing of xt through ht in time is convolution. Yt equals ht convolved with xt. We have seen that if we have converted the signal via continuous time Fourier transform, we have xf, the representation of the signal in the frequency domain. Similarly, ht can be changed to hf. And interestingly, convolution in time becomes multiplication in frequency, which is a much simpler process. Similarly, in the discrete time domain, xn can be converted into x omega, hn can be converted to h omega, and the convolution in time again becomes multiplication in frequency. What do you need to take note of? In n, here is discrete time, so n is an integer only compared to xt, where t is real. What else you have to take care of is that the frequency is radians per sample. It means that because time is an integer, every sample index, how time progresses will affect the signal. And in the digital domain, what we are thinking about, when one sample changes, how much radian changes. So frequency is in radian per sample unit. This is different to here. Here frequency is cycles per seconds, where seconds is time and time is continuous.